Okay, hello. I'm here with my roommate Max, and we are going to go over the first problem from the fourth homework assignment. Um, yeah, so it's about wind power. So let's get started. Consider a rectangular area with width 1 meter and a height stretching from 20 meters to 200 meters above the ground. We're going to use a rectangle instead of a usual circle to simplify the math. The wind speed at h equals 10 meters is 20 meters per second. Suppose that that is true, and that the wind speed varies with height according to the h/17 law, which I have here. First, we're going to find the average speed of the wind. So this equation, v of h, this tells us how fast the wind is blowing at a given height
Right.
based off of this initial, it's 20 meters per second at 10 meters. So we are to find the average speed over height from 20 to 200 meters. What we're going to do is we're going to integrate to find the total, sorry, the total area bound by
Under the
the
curve.
axis. Yes, the
Right.
curve from 20 to 200, and then we're going to divide that by the difference between the two to find the average. So divide it by 180. So yes, we're going to have the integral 20 to 200. And then we're just going to plug in that v of h equation and substitute in the things we know. We know that v initial is 20, and we know that h h is what we're the variable we're integrating around, right?
Right.
So h, and then we know h initial was 10,
10,
and so then we're going to put that
1,
to the
7,
1/7
dh.
dh. Yes.
We're going
Um.
to divide that by, right?
Yes. 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 And then we're going to divide that number by
200 minus
200 minus 20, which is 27.68. Good visualization for this is, let's see, I'm just going to graph this right here. There is our wind speed graph. It's in blue here. I'm going to submit a picture of the
Oh,
Desmos
okay.
afterwards, so we'll have that too. Um,
Wind speeds are pretty low over here.
yes, luckily we're not. We're starting our integral at 10, so we're all good there. Um, yeah, so that's that first problem. We got our average speed in the wind is, make sure to
27.68.
add your units.
Oh, what are
It's just,
the
it's just
units?
meters per second.
Okay.
Right. So now we need to find something called the mean cube speed of the wind. And this requires some context into why we're going to find it. And it's that we're going to actually look at the next problem because we're going to need it there. That's what this thing is right there.
VT to the power 3.
Yeah, VT. That means we're not just cubing the equation. We
Mm-hmm.
are going to cube it, integrate it, and then take the cube root of it.
Oh,
Because
okay.
because we want the higher wind speeds to have a higher weight, effectively, if that makes sense. How we're going to do this is we are going to do the same integral as before,
20 to, or
20 to
20 to
200.
200.
Yeah, this is question B now. Yeah. Um.
And it's 27.68.
No, we're actually gonna have to. I think we're just gonna have to do the equation
The
again.
whole equation again? Aren't we just taking the cube of it though?
We are gonna cube it. What we're gonna do is we're gonna put parentheses right here, and then we're gonna put a cube right there, and then at the very end, we're gonna put everything to the one
To the
third.
1/3, yeah. Okay.
Yes.
Okay, so that'll be 20 times h divided by 10 for 1/7 dh and
Mhm.
parentheses 1/3 or no 3.
3, yeah.
So cube it.
No, the cube is within the parentheses because we want. Okay, so what we want to do is we want to cube all of the wind speeds. We basically want to cube this graph right here.
I just put my parentheses in the wrong place.
Oh,
I
okay.
put the dh inside what was being cubed.
Yes. Yeah. So because the equation for power, it wants to know it's based off of the v cube. So for then taking the average, you just have to do it
Right. And
this
then
first
that whole thing is in brackets to the 1/3.
after you divide it by 180.
Oh, I forgot to go to
Yeah.
one.
So
Divided by 180, and then big
big
parentheses
parentheses to the one
to
third.
the 1/3.
Sweet. And that gets us a very slightly different answer of 27.861. Okay, so starting with part C here, we're gonna find the average power in the wind. And so the equation for that is average power equals zero point 0.5 times the density of air times the area that we have times the velocity cubed.
What's the
Because
density of air?
density of air is going to be 1.293. Um, so this is very similar to
Is
the
that dense or not dense?
it's 1.293 kilograms per meter cubed. So a meter
That
cubed
seems pretty not dense.
is like
That's pretty big.
there, and it's like I mean it's for air. It's
Do you
kind
know
of
how dense
dense.
a person is?
Very.
Well, you're very dense.
Okay. Um, so this is very similar to
The
uh,
last problem with B.
yes. If you know the equation for kinetic energy, this is quite similar to it. The equation for kinetic
I have no
energy.
idea what that
Okay, well
equation is.
it's 1/2 mv squared. That's just
Okay,
how much energy is in something that's moving because it's moving. Um, like my pencil gets kinetic or my pen gets kinetic energy when I do that.
it's 1/2 mv
One
squared
half the 1/2 mass times velocity squared.
is
It's
outputted in.
it's just energy is just how
But
much
what's our measurement of energy for this?
joules.
Joules?
Yes.
Okay,
I'm converting calories to joules there.
very cool.
Yeah.
Okay,
This is going to be it's going to be v cubed because uh we don't simply care about the energy in a given mass of air. We care about how fast we're processing that mass of air as well. And that's how fast it's moving, right? So
okay,
if let's say I have a meter cubed of air right here and it's moving at a certain speed, but then I want to know how fast I'm experiencing that. I got to multiply it by the velocity again.
okay.
So it's like how fast are you going to process this cube of air? There's that's you multiply by the velocity again. Okay, so we're going to use a
Does
very similar equation as last time, as in part B, except we are just not going to do the final
the
cube root,
final cube root?
right?
Yeah,
Because we actually just care
we just
about
care about cubing it.
cubing the wind speed because we care about it to the third power, right? Because mv squared
Yeah,
multiply it again.
that's what it says on the law, but
Yeah.
because it's different for gases than
No, it
solids.
would work for water too.
But it's mv squared. Why is it mv cubed?
If I have a really fast moving thing of air, but let's say it's vibrating. It's
Okay.
vibrating back and forth really
Yeah,
fast. It
it
has a
does
lot of
that.
kinetic energy, but if it moves through you really slowly, the rate that you are getting kinetic energy is really slow, as opposed to if I have the same vibrating this way and I'm throwing it at you at 100 meters per second, then you're getting a lot more, a lot faster.
Okay, so it's like the second degree of the speed almost.
Sure, whatever helps you think of it. I'm not sure what
Because,
you mean by that,
well,
but
because like what you're describing is all the things are moving really quickly, and that's
yeah,
like one measure of speed, but then the measure of how
that's a
they,
measure of energy.
okay, right.
Energy and
It is a
speed are
measure of
different
energy.
things.
Fair enough.
So energy is the speed cubed, 1/2 mv squared, and then you care about how fast you're receiving that energy, which is multiplying it by v again,
Which would bring us to cube.
which would bring us to cube.
Okay, okay.
Cool. So that is going to be
Well, no, hold on. I have to
yeah,
think
you got to
about
write out the whole integral still. So it's going to be zero point 0.5 times 1.293
times
times
180
180
times the integral from 20 to 200 of 20 times h divided by 10 to the 1/7 to the third
dh
dh
over 180.
divided by 180.
Yes.
Not times 1/3.
No.
Get rid of that. And that gives
And that
us,
gives
oh,
us
fuck, yeah, freaking lot.
2.5 million watts or 2.5 megawatts. So you can do a capital M and a W.
2.5 million watts.
Okay. Yeah.
Does mega directly translate to million?
Yeah. I think you should know this in chemistry. M is 10 to the sixth. Big M's mega,
Yeah,
milli,
but I
kilo.
we
You don't
under
go in order.
OCAP we stopped
Oh,
using
okay, fine.
the
Okay.
molar mass or no, not
Okay.
molar mass.
You stopped doing math. How long?
Avogadro's number.
Okay.
We stopped doing that a while ago.
You stopped doing math.
Yeah, math is over. We just draw.
So a watt, the joule per second. My bad.
Joule per second,
Yes.
and the joule is you explain this to me. Moving
Yes. A joule is
a
moving
meter,
a
a
kilogram,
kilogram, a meter.
kilogram a meter.
A meter's kind of a long
Yeah,
way.
a joule's
Joule
not
feels like a lot of energy.
Yeah, but we have a huge amount of
I
air.
mean, yeah, but like how many joules do I exert normally, like to live?
Um, I don't know. Let's convert calories to joules. You eat 23,000 calories.
23,000 calories?
That's that many joules. So
Those are kilocalories.
that's normal calories. That's like food
That's what we
calories.
count.
Yeah.
Yeah, and then
So
it's called
you
kilocalories in other places.
so
That's
that's
a lot.
yeah. So you eat enough. This is 2.5 megawatts. This is this
So
much, but this is every
this
second.
is every second because it's
Yes.
watts.
So that's effectively it's making us 600 calories per
600
second.
calories per second.
Yeah. You think about it, you got a giant spinning blade up in the sky.
That's pretty
I
cool.
mean, calories are chemical energy, so it's different, but
It's still pretty cool.
yeah. Cool. Okay. So,
We're on D now.
yes, now we go on to D,
Extractable.
available or extractable power in the wind. So this will be a pretty simple step. All you're going to do is you're going to take your previous answer and multiply it by 0.59.
So I just have 2.5
Yeah,
megawatts. That's what
2.5.
I wrote down.
Yeah,
We don't
2.5
have to go
megawatts
any
is
more
fine.
specific
No,
than
no,
that.
no, that's fine.
Okay.
This is all, like I said, this is all very approximate anyways. We're using a rectangle. And wind speed in reality does not perfectly follow the h to the 1/7th law. It's much more complicated. So
Oh, good. I'm glad.
yeah.
And it's
And so it's
available
0.59.
power,
Yeah. So
extractable power.
0.59 is because it's this thing called the Betz limit, and it's when you have a turbine in a fluid or a gas of any sort. Um, Basically, if you take all the energy out of the stuff before the turbine, it's going to have to start basically pushing the stuff after the turbine because that stuff will have no energy, and now you're losing energy before. So like
Okay.
think of it as
It's like a buildup.
think of
Like
it
it's like a stream that has to keep going.
yeah.
Otherwise, if you just put like a wall there, I guess this is a bad
Right.
example.
No, I mean you're kind of right. You can't impede it too much. You
Or
can't.
it won't flow properly.
Okay,
It'll build up.
here's you. Let's say you got a pipe, you got a propeller in the pipe, just for the sake of like
Right.
your shit can't, you like, sorry, your stuff can't go anywhere else.
Yeah.
It's fine, you won't care. The water can't like go around the turbine. It has to
It
go.
has to go
It has
through
to
it.
go through.
Can't go
So
over it. Can't go around it.
no,
Gotta go through it.
yeah,
Okay.
as the water before the pipe has energy. It has kinetic
Right.
energy. It's in motion.
That's what we're taking.
Yes, if we take the motion out. Okay, so here's something
There'll
important.
be no motion,
Normally,
and that's bad.
yes, normally behind windmills, you see lower wind speeds, right? That
That
makes
makes
sense.
sense
That makes
because
sense.
the energy from the wind is being
Right.
absorbed by the
So if
propeller.
if wind speed was zero after after the wind turbine,
Okay.
yeah, the propeller. If wind speed was zero, that means yay, we got all of the energy out. But now we still have this wind over here at 20 meters per second, and now we have a huge mass of air that's not moving right here.
Right. And
It can't go anywhere.
that doesn't work.
No, I mean like then this will like start bouncing back off, and then it'll just like kind of go off
Messes
that
with the
way.
flow.
Yeah, it messes with the
It
flow.
also
So
seems
basically,
really hard to set the wind or the energy of the wind to zero.
right. It's basically impossible. So we through basically
So Betts did an equation and found that
yeah.
it was
It's actually it's
59%.
an optimization equation where
Okay.
you do the it's about I think you do the extractable power of the wind, and then you do energy after and energy before, and because and then you optimize for extractable power, if that makes sense.
Okay.
Because the wind has a kinetic energy before, the wind has a kinetic energy afterwards,
Afterwards.
and conservation of energy tells us that it must be kinetic energy before, power we extracted plus
Plus
kinetic
kinetic
energy,
energy
and you
afterwards.
optimize that, and it's at 0.59. You want to
Because
take
energy can neither be created or
there
destroyed.
you go, there you go.
Okay, so when we put that
So you just
in,
multiply by 0.59. It's a really easy step that sounds really complicated. So 2.5 times 0.59
9
is 1.47 megawatts.
million watts.
Yep.
Megawatts.
And that is the
That is question one.
yes, that is we're not doing any more questions. Just that one.
Oh, good.
Yes. Oh, don't worry. Just doing that.
Dang.
So that's the
Boom.
average power available in the wind at this location
With our rectangle.
with our rectangle. Yeah, we could do a circle. We could go back and do a circle.
I don't think we need
It
to
would
do
just
a
make
circle.
it would just make the integral more complicated. Anyways, that's all. Thank you.